Hello, Algebra 2, and welcome to this Chapter 3 for Review number 2 video. We did problems 1 and 2 together in class, so I'm starting this video on problem number 3. So we were supposed to solve each of the following inequalities and show solutions on a number line. So the first thing we should do to solve an inequality is to solve an equality, to find out where these things are equal, or find the boundary points. What makes 2x minus 1 absolute value equal 5? And so we'd say, okay, that would mean 2x minus 1 would need to either be 5 or 2x minus 1 would be negative 5. And solving each of these separately, I get 2x would equal 6, so x could be 3. So 3 is a boundary point. And I'll fill that in, make that a solid circle because we have an or equal to option up there. And if I add 1 here, I get 2x would be negative 4. And so x equaling negative 2 would be the other boundary point. And so we know that 2x minus 1, the absolute value of it, is greater than or equal to 5, either over here or in between or over here, or some combination thereof. So let's go ahead and test some values and see what happens to make this inequality true. Suppose x is, say, negative 4. Well, if x is negative 4, we get the absolute value of negative 8 minus 1. Is that bigger than or equal to 5? It absolutely is, so we know that this region over here makes the inequality true. I could test 0. 0 is convenient. If x is 0, I get the absolute value of negative 1. It has to be bigger than or equal to 5. And that is definitely not true. So I know the region in between negative 2 and 3 must fail. And I could test positive 4. If I test positive 4 in my original inequality, I get 8 minus 1 absolute value. Is that bigger than or equal to 5? And it most certainly is. So gosh, this region seems to work over here. Graphing your solutions on a number line is not sufficient. You need to actually write the inequalities that are solutions. And so our inequalities would be all values of x that are greater than or equal to 3, or x could be less than or equal to negative 2. Moving on to part B. I had to revise the worksheet, so if my part B is different from your worksheet, you can go ahead and change your part B to be like mine. I think the middle value here might be different. So let's see. Again, before you solve an inequality, it's best if you solve an equation to find some boundary points. So I'll factor this thing. You get 2x and x. And to get a negative 1x in the middle, I'm taking a 3 here and a 5 here. That's 5x. That's 6x. So if that's negative and that's positive, we get negative 1x in the middle. And let's see, if I'm solving for where this equals 0, that would mean x could equal 3, or x could equal negative 5 halves, which is negative 2.5. So these are my boundary points. Negative 2.5 is a boundary point, and positive 3 is a boundary point. And I'm making this an open circle because it's strictly less than 0. And now I know that either the region over here, or the region in between my boundary points, or the region over here, or some combination thereof, must make this inequality true. So let's start testing some things. Let's say I test negative 4. If I test negative 4 in this inequality, well, I think actually it's going to be easier to test it in factored form. So I want to know where 2x plus 5 and x minus 3 is less than 0. So if I test negative 4 in here, I get negative 8 plus 5, so negative 3 times negative 7. Is that less than 0? And no, it is certainly not. So this area over here fails. If I test 0 in this inequality, we get 5 times negative 3. Is that less than 0? And yes, it is. So this middle region seems to work. And we could test positive 4 over here. Positive 4 here, I get 8 plus 5, so 13, and 4 minus 1. 13, or 4 minus 3. And 13 times 1 is definitely not less than 0. So this over here fails. So plugging in values is a way to check quadratic functions like this, functions involving x squared. But also, you could just think of these things as being parabolas, meaning when we solved the equation and said x equals negative 2.5 and x equals 3, what we did is we found the x-intercepts of a parabola at 3 and negative 2.5. And since my leading coefficient is positive, I know the parabola must be right side up. If you look at this equation, really this is just asking us, where is the parabola less than 0? Well, here's the line 0, where y equals 0. And so definitely between negative 2.5 and 3 would be the solution. Just like in the last problem, graphing things on a number line is not sufficient. We would need to write a solution. X must be less than 3 and greater than negative 2.5. Moving on to part C. Part C, so again, I'll find some boundary points. I'll write absolute value of 4 minus 3x equals 2. And so that would mean 4 minus 3x would either be 2 or 4 minus 3x could be negative 2. And if I subtract 4x from each side, I get negative 3x would be negative 2, or x would be positive 2/3. And here, subtracting 4 from each side, I get negative 3x could equal negative 6. So x could equal positive 2. So we have a boundary point at positive 2. Whoops. Boundary point at positive 2 and a boundary point at 2/3. All right. I know I'm not very good at like that. I'm putting an open circle because this is strictly less than. And let's test some values. Let's test, say, negative 1. If x is negative 1, we'd get absolute value of 4 plus 3. Is that less than 2? No. So negative 1 is a fail. We could test positive 1. When x is positive 1, I get 4 minus 3. Is the absolute value of that less than 2? Absolutely. So this region in here seems to work. And we could test 3 just to make sure, but I think I see a pattern here, and I'm pretty sure that 3 is not going to work. 4 minus 9 is not less than 2, so this area over here also fails. So we would write our solution. X must be less than 2 and greater than 2/3. And last but not least, number D. And I think, well, no, D is the same as what's on the worksheet. Okay, so again, we'll solve an equation where this equals 0. A 3x and an x, and I'd try a 5 here and a 1 here. Well, I get a 2 in the middle to get a positive 2 plus and minus. And so x must equal 1, or x must equal negative 5/3. And so my x values, these are my boundary points, my break points, positive 1 and negative 5/3, which is negative 1 and 2/3. So about there-ish. And let's see, this is a parabola. We want to know where the parabola is greater than 0. And since we just found some x-intercepts, I'm thinking that my solutions must be from when x is above 1 and when x is below negative 1 and 2/3. Because in this region, it's above the x-axis. My graph is above the x-axis. But that's just me basing things on a graph. Here, I'm going to fix this. I probably should be thorough and check some points. There we go. So maybe I'll check where x is 0. Does 0 make this thing true? Well, if 0 makes this thing true, we'd have 0 plus 0 minus 5 is greater than or equal to 0. And that is not true, so in here is a fail. This region is a fail. So yes, I am going to conclude that the other two regions must work. And so my answer would be x could be greater than or equal to 1, or x could be smaller than or equal to negative 5/3. Moving on to number 4. So on your worksheet, there were directions to number 4. Whoops. There, I just went and grabbed them. And what the directions said is to solve the following systems either algebraically or graphically. So either by using algebra or graphing, and then by actually testing your answers to make sure that they work. So maybe you tried to solve this thing algebraically, and if you did do so, then you would have written, well, this stuff equals this stuff, and so you would have said the square root of x plus 3 plus 1 is supposed to equal 1/2 times the absolute value of x plus 1. And you could try and try and try, and I'm not really certain that there's a good way to go about solving this equation algebraically. It might be so, but it sure seems like a hassle to solve an equation that involves both a square root and an absolute value. That said, these directions are a trick. They're a trick because I say that I'm giving you a choice, either algebraically or graphically. But the fact is, all of these are meant to be solved graphically, because if you try to do them algebraically, it's just ugly. So you should graph these things, and I'm going to encourage you to get out your toolkits and try to do this on your own before you just take a look at what's on the video. So looking at that first green boxed equation, it is a half sideways parabola, and this is shifted backward 3 and up 1. So my locator is -3, +1, and it's a sideways parabola. So over 1, up 1, over 4, up 2, and over 9, up 3. And we've got ourselves a half sideways parabola. And if I take a look at what is in the red box here, that is an absolute value, and it is just shifted up 1 unit. So let's shift it up 1 unit. There's my locator point, and it's got a slope of 1/2. So rise 1, run 2. Rise 1, run 2. Why did I do that in red? Let me fix this and color code these things. This guy should be in green. Going all Christmassy colors here. There we go. And the absolute value should be in red. There we go. Up 1 over 2, up 1 over 2. All right. And if you graph this thing accurately, you have 2 solutions because these graphs cross in 2 spots. They cross at this point here, which is -2, 2, and at this point here, which is 6, 4. So you should test these points to make sure that they work in either equation. So if I test, say, -2, 2 in each of these equations, let's see, my y value would be 2. So looking at the top equation, 2 must equal the square root of -2 plus 3 plus 1. I believe that works. 2 must equal the square root of 1 plus 1. That works. Testing it in the bottom equation, I'd get 2 is supposed to equal 1/2 times the absolute value of -2 plus 1. Or 2 must equal 1 plus 1. Whoops. And that also works. You should also test 6, 4 in your equation. So let's see, my x is 6 and y is 4. So testing it in the top equation, I'd get 4 is supposed to equal the square root of 6 plus 3, which is 9, so 3 plus 1. That works. And also 4 is supposed to equal 1/2 of the absolute value of 6. So that much is 3 plus 1, and that also works. Moving on to number 5. Number 5, again, we have a choice of solving this algebraically or graphically. And if we were to solve it algebraically, we'd have y plus 1 squared minus 4 equals the absolute value of x minus 3. So we've got this squaring and absolute values, and it just looks so confusing, and I think I'm going to not try to do this algebraically and just solve it graphically. So again, we have two functions. I'm going to graph the easy one first. Absolute value is simply shifted down 3. And it's got a slope of 1. So that function would look about like that. And the top function is a horizontal or a sideways parabola. And so you might want to look in your toolkits at this point. The parent equation for those are x equals y minus k squared plus h with a locator of hk. And that's something you could just copy right out of your toolkit or look at in your toolkit. What that means is that our value for h, this h, is that -4. So our h value is -4. And it's supposed to be y minus k. We have a +1, which means our k value is -1. So our locator is -4, -1. So I'll go back 4, down 1. So that's the vertex of our sideways parabola. From this vertex, we can just graph a regular parabola. So over 1, up 1, forward 4, up 2, or down 2, forward 9, up 3, or down 3. And if we graph this well, we should see that we have 1, 2, 3 points of intersection. And so those 3 points of intersection are, see, -3, 0, that's this one, and 0, -3, that's this one, and 2, 4, 5, 2, 5, 2. That's that one. And then we should check them. So checking -3, 0 in both equations. Here's my x, here's my y. -3 is supposed to equal 0 plus 1 squared minus 4. Well, I can look at that and know it's true. Looking in the bottom equation, -3 is supposed to equal the absolute value of 0 minus 3. That's also true. So I could, whoops, uh-oh. There we go. There, I can organize my work this way. Checking 0, -3. Here's my x and here's my y. So in the top equation, I would get 0 is supposed to equal -3 plus 1 squared minus 4. Or 0 is supposed to equal -2 squared minus 4. That definitely works. The bottom equation, it would be 0 is supposed to equal the absolute value of -3 minus 3, and that also works. So those guys are. And testing this last point, here's my x, here's my y. It would be testing the first equation. I feel like I blew it. I did blow it. I blew it right here. I reversed things. I might have even done it here also. Looks like I did. Yeah. Taking this first point in the lower equation, I reversed my x's and y's. It should have been 0 equals the absolute value of -3 minus 3, which also works. So there was that. Let's see if I'm allowed to shrink it down. All right. And in this one, it would be y, negative 3 must equal the absolute value of 0 minus 3, which also works. Crazy. Okay. So now, checking that last point, if x is 5, we would get 5 must equal 2 plus 1 squared, that's 9, minus 4. Well, that I know is true. And then in the bottom equation, it would be 2 must equal the absolute value of 5 minus 3. That also works. So all points check out. Taking a look at number 6. So again, we're going to solve this graphically. It looks like we have a circle and an exponential function right here. So starting with the circle, this guy is shifted, the center is shifted forward 2 and up 2. So the center is at 2, 2. So there's our center. And if the radius is the square root of 1, then the radius is 1. So up 1, down 1, back 1, and forward 1. And we have a little tiny circle right there. Okay, now to graph the exponential function, the parent equation for these exponential functions is y equals 2 to the x minus h plus k. Our locator is hk. Well, our h is definitely 2, and our k is definitely 0. And if you were to check in your toolkits, I called that 2, 0 the new origin, and I had you make an open circle there and draw an asymptote through there, because the asymptote does pass through the origin on the parent function. And if you were to look in your toolkit, the xy table that you'd be graphing has a 0, 1, a 1, 2, a 2, 4, a 4, 8, and a negative 1, a half. Those would be points from the origin. So if this little spot here is our new origin, the first point we would do is 0, 1. And 1, 2 would be right here, and 2, 4 would be up there, 4, 8 would be up that way, or negative 1, a half. And so we get our swooshy function. There she is. This has 2 points of intersection, and those points are 2, 1, right there, and 3, 2. So checking them in each equation, checking 2, 1 in the first equation. That would be 2 minus 2 squared plus 1 minus 2 squared is supposed to equal 1. And I can look at that and know that this is going to work because that's 1. And my second equation would be 1 must equal 2 to the 2 minus 2. And that's 2 to the 0, so that also works. Checking this point here, the 3, 2, I would get x, no, not x, that's the whole point. Plug in 3. 3 minus 2 squared plus 2 minus 2 squared. Does that equal 1? And this is 1, and that's 0, so yep, that works. And 2 must equal 2 to the 3 minus 2. And that is 2 to the first. So that works. Yay! Everything works out. And let's move on to number 7. Number 7 said, solve the following systems of equations first algebraically. Okay. Well, we could go ahead and set things equal. And it's not going to be pretty, but we'll survive it. Equals negative x minus 2. I think what we should try to do always in solving absolute value problems is isolate the absolute values. So get everything else on the other side, no matter what it costs us. So let's start by adding 3 to each side. I get 2 times the absolute value of x plus 2 must equal negative x plus 1. And we could divide both sides by 2. And that gets us the absolute value of x plus 2 must equal negative 1/2 x plus a half. And from here, believe it or not, you can solve this like a regular absolute value problem if you have the absolute value of something. Here, some crazy colors. If I have the absolute value of something equals this stuff, then what's under my circle must either be the positive or the negative of this stuff. And so I can write two separate equations. I can say what's under that circle is either going to have to equal negative half x plus a half, or what's under that circle is going to equal the opposite of this, which is positive 1/2 x minus a half. And what's under that circle is, ta-da, x plus 2. So you have some equations to solve. They have fractions, and so I think the first thing I do, no matter what, is multiply both sides by 2 to eliminate my fractions. I get 2x plus 4 equals negative 1x plus 2. Did I blow that? Yes, I did. 1/2 times 2 is not 2, it's 1. Okay, and multiplying by 2 here, we'd get 2x plus 4 equals 1x minus 1. And now we solve. I could add an x to each side. I get 3x, 4. 3x equals negative 3, so x could be negative 1. And over here, if I subtract an x from each side and also subtract a 4, I get 1x plus equal negative 5. So I have x is 1 and x is negative 5. I'm solving a system, which means I should find some y values, and I'm going to use this equation. Y is negative x minus 2. Y is negative x minus 2. So for this point, y would be the opposite of x, 1, minus 2. So y would be negative 1. So I'm thinking one point of intersection is negative 1, negative 1. And here, y is going to be the opposite of x, minus 2, so that's 3. And the other point of intersection is negative 5, 3. So I think I have some points of intersection. This is just a big mess, and I'm going to try to clean up. Okay, and now we're supposed to solve this thing graphically. And if we did our math right, our functions should cross at negative 1, negative 1, and at negative 5, 3. So let's just graph these things. Top function. The top function is an absolute value function shifted backward 2, down 3. So backward 2, down 3, and it has a slope of 2. So rise 2, run 1, rise 2, run 1, rise 2, run 1. And we've made our V. And so far, so good. The absolute value goes through both of our intersection points. And the other function is a line with a y-intercept of negative 2 and a slope of negative 1. So backing up, it also passes through both of the points that it was supposed to pass through. So hip hip hooray, yay us. Moving on to number B. Yeah, number 8. Number 8 says, solve this thing algebraically. Okay, well, if we're solving this system algebraically, we'd write 2x equals the square root of x plus 3. And I would probably square both sides. And if we square 2x, we get 4x squared. And if we square a square root, we get what's on the inside. And so I get 4x squared minus x minus 3 equals 0. I factor away, I'm thinking 4x and x and a 3 and a 1 to get a negative 1 in the middle. Let's see, this is going to be positive 3x, and this will be positive 4x. So if I want negative 1x, I'd want the 4 to be negative. So negative, positive. And I think we've got this factored. And we could write a couple of answers. We say x must be negative 3/4, or x could equal 1. Well, I know there's a little trickery coming up here. And if you're a clever cookie, then at this point, when you're solving this problem, you would check your answers and make sure that they actually work in both equations. When x is negative 3/4, do these two equations equal each other? So maybe I'll give it a whirl. If x is negative 3/4, I'd get 2 times negative 3/4. Does that equal the square root of negative 3/4? Oh, this is not fun. Plus 3. Well, 2 times negative 3/4 is negative 6/4, which is negative 1.5. And if I take the square root of negative 3/4 plus 3, well, that's the square root of 2 1/4, or the square root of 2.25. And I don't even need to know what the square root of, that's 3/4. I don't need to know what the square root of 2.25 is, because whatever it is, it's a positive number. This is positive. And over here, this is negative, and they do not equal, which means this answer of negative 3/4 is extraneous. Extraneous. I think that's how it's spelled. It would be wise to check 1, to check where x equals 1 and verify that that does work. If x is 1, we get 2 times 1, which is 2. Does that equal the square root of 1 plus 3? And 2 does equal the square root of 4. So 1 definitely works. This is going to be verified by our graph. Let's see, if we're going to verify that these are the solutions, well, we would graph these two functions. Y equals 2x is a line. Actually, I'll color code these things. Here. Y equals 2x is a straight line with a slope of 2. So it looks thusly. And y equals the square root of x plus 3 is half a sideways parabola shifted back 3. And sure enough, I guess I can't scoot this thing over, but sure enough, these two functions intersect exactly one spot where the x value is 1. So there's only one solution to this system of equations. Moving on to number 9. Number 9 says add, subtract, multiply, or divide. Okay. So here we are adding some fractions. To add fractions, we need to have a common denominator. So I would need to take the top of this fraction and multiply by x plus 1, assuming I do the same thing in the denominator. And I would need to take the top and bottom of this fraction and multiply by x minus 2. The numerator of the top fraction just became 3x squared plus 3x over some stuff, minus 2x minus 4 over some stuff. And now that we have a common denominator, we can combine the numerators, but just keep in mind that this negative sign applies to the entire package of that numerator. And so what we get is 3x squared plus 3x minus 2x and plus 4 over a bunch of stuff. And that cleans up a little bit. 3x squared plus x plus 4 over x plus 1 times x minus 2. And it would be a wise thing to check and make sure that the top, the numerator, does not factor. So let's see, I could try to factor. It's going to be 3x and x. And 4 is either going to be 4 and 1 or 2 and 2. But I don't think any way that I slice it I can get a positive 1 in the middle, because these guys are going to have to be either both positive, both negative. I don't think it's going to work in any way we try it. That's not going to get me a 1 in the middle. Or if I try a 4 here and a 1 here, one of these, this would have to be negative to get a negative 3x and a positive 4x to get that positive 1 in the middle. And that would multiply to negative 4, and I don't have a negative 4. Long story short, the numerator does not factor, and so we just have an answer, which I'm now going to rewrite, of 3x squared plus an x plus 4 over x plus 1 times x minus 2. And that's all we can do. Let's move on to part B. Part B. Okay, well, we again need a common denominator, and I think it might help us to factor the denominator of this second fraction. Let's see, that factors to x plus 4 and x plus 1. So to get a common denominator, what we really need in our first fraction is a multiple of x plus 1 on the top and the bottom. So I'm going to put that in. Now my first fraction has become x squared plus x over some stuff minus 12 over the same stuff. And I just realized I made a little mistake up here in part A. I'll go back and fix that in a moment. But we've got x squared plus x minus 12 over x plus 4 and x plus 1. And I'm hoping you notice that the top of this fraction does factor. It factors to, let's see, x plus 4 and x minus 3 over x plus 4 and x plus 1. And looky there, our x plus 4s doth cancel. And so we end up with x minus 3 over x plus 1. And so the fact is, this does equal x minus 3 over x plus 1 with conditions. I forgot about the conditions. And the conditions are that all fails if x is negative 1. And also all bets are off if x is negative 4, because we would have 0 in the denominator. So we'd have to say x cannot be negative 1 or negative 4. And now I bet you know what mistake I made there with problem A. I forgot my excluded values. So going back to part A, I would say that this is true as long as, comma, x does not equal negative 1 or positive 2. So let's throw that into the mix. All right, let's take a look at part C. Part C says, figure this one out. Okay, well, we've got a bunch of stuff, and it looks like it all needs factoring. So let's try to factor the top. Factoring the numerator of this thing, 3x, x, 5 and 2, I believe will get me 15 and 2. And if they're going to add to negative 17, I think they would both have to be negative. The denominator does factor. I have a common term of 2x. So if 2x comes out front, what would be left on the inside is 3x minus 2. We're multiplying this thing by x plus 3 and x plus 5 over x plus 5 times x minus 5. And it might be a really good thing at this point, before we go canceling things, to think about our excluded values, because we're about to get an answer. Whoops. So we're going to get an answer for what this thing equals, provided x does not equal. So what would make this whole thing undefined? Well, if x is 0, this first term would be undefined, so x can't be 0. If x is 2/3, then we have 0 divided by 0, so it can't be 2/3. Can't be 5 or -5, and it also can't be +5. So positive or -5. So erase that stuff. And now cancel some things. Whackety whackety. Whackety whackety. Ooh, whackety whackety. I think we've got ourselves an answer. This must equal x plus 3 over 2x, provided x is not 0, 2/3, or positive or -5. Group and shrink that baby down. Let's take a look at D. Again, it's another division problem, so let's just factor like crazy. The top of this thing does factor. It's a factoring pattern that I'm hoping we're getting good at recognizing. If you think about 25x squared, that probably came from 5x and 5x, and -4 came from +2 and -2. And when you take a look at what your middle values would be, you'd get a positive 10x and a negative 10x, and they'd cancel each other out. So, yay us. Okay. Over here, this is x plus 3 and -1 divided by, this top has a common term. We could pull out a 2x, and what would be left is 5x plus 2 over x plus 2 and x plus 3. I think this would be a very good moment to think about what our excluded values would be, because we know we can't divide by 0. So, let's see. My excluded values, I can't have x as -3, so x cannot be -3, x cannot be +1, x cannot be -2, and x cannot be, I already have the -3. Okay, so I don't need to worry about those. Now, when we take the reciprocal of the second fraction, we're going to end up with some more excluded values. So I now have a, oops, I forgot to take the reciprocal. We're now going to end up with a 2x in the denominator and a 5x plus 2, and x plus 2, and x plus 3 on the top, and 5x plus 2, and 5x minus 2, and we'd have an x plus 3 and an x minus 1. Okay, well, now we can cancel some things. Those guys are going to go away, these guys are going to go away, and I think that's it. So I think we have an answer of 5x minus 2 times x plus 2 over x minus 1 times 2x, provided x doesn't equal any of those values. Because this is a test review, I'll just let some of you guys know, on your test, I am going to give you a problem like number 10, just as a reminder to go back and identify excluded values. Whoops, problem 7 above, it's supposed to be problem 9 above. Sorry about that. So on your test, you will get a little reminder prompt to go back and write in what your excluded values are. So you don't have to put them in on a problem like this unless specified. So I could go ahead now and fill these things in. Let me clean up my screen. Okay, so if we were filling these things in, the problem 9 above, the excluded values would be -1 and 2. For B, it would be -1 and -4. Here we had 0 for C, 2/3, positive or -5, And here we had negative 3. Ooh, did I forget? I did. I forgot my other excluded value. Bad, Signorati. My other excluded value would be negative 5 halves in here. So negative 5 halves. And I got that excluded value when I took the reciprocal of the fraction. Don't know what I was thinking. 1, negative 2, and negative 5 halves. Okie doke. Moving on to number 11. Number 11 says solve a bunch of equations for x and be sure to indicate which answers might be extraneous. Okay, well, it is always good to think about excluded values first. We have an excluded value right off the bat of negative 4. X cannot equal negative 4. That's the one thing we know for sure. So x can't equal negative 4. That said, notice we have a common denominator. So if I told you that, say, A over B equals C over B, I'm pretty sure you could conclude that A has to equal C. Just because we have x's in a problem doesn't make it any different. If I have 3x over something equals x minus 8 over something, then 3x must equal x minus 8. And so I could go ahead and solve this problem and subtract x from each side. Scribble that out. We have 2x equals negative 8. Divide by 2, and we've got ourselves an answer. X equals negative 4. Hey, wait, didn't I just get done saying that there's one excluded value in the world, and that's x can't equal negative 4? It's true. So the only answer to this problem is x has to be negative 4, but we know x can't be negative 4 because that makes this undefined. So the final answer for this problem, tricky, is no solution. It's not possible to solve it because the only number that works in the numerator is negative 4, and negative 4 will not work in the denominator. Mean, tricky problem. Let's take a look at problem B. Problem B. Well, we're solving a problem involving square roots, so we've got to be careful to make sure that any x value we get doesn't make the inside of that square root a negative number. Alright, so we have the square root of 3 minus 2x plus 3 equals 8. We blindly go forward and subtract 3 from each side, and we get 5. And we think to ourselves, Miss Signorati won't trick us again, will she? So we square both sides, we get 3 minus 2x equals 25. Subtract 3 from each side. Negative 2x equals 22. And divide by negative 2, and x equals negative 11. We think, okay, will that make this an unreasonable solution? Let's check it out. We would get the square root of 3 minus 2 times negative 11 plus 3. Does that equal 8? Well, negative 2 times negative 11 is positive 22. 3 plus 22 is 25. And looking at this thing thusly, I'm pretty sure our answer is going to stay. All right, let's take a look at part C. Part C, solving problems that involve absolute values. Again, those can be tricky, so we should make sure we check our answers. So we have negative 3 times the absolute value of some stuff plus 9 equals negative 27. Maybe we're smart and we subtract 9 to start with. So we get negative 3 times the absolute value of some stuff equals negative 36. And if we divide through by negative 3, we get the absolute value of 5 minus 2x equals 12. And now we can solve this thing. We could say, okay, what this means is that either 5 minus 2x must be 12, or 5 minus 2x must be negative 12. And we can solve these separately. Subtract 5 from each side. Negative 2x has to equal 7. Oh, why did I do this to me? So x would equal negative 3.5. Or here, negative 2x would be negative 17. So x would have to be positive 8.5. So we get these two answers. And I guess I should check them and make sure. Actually, I don't think I need to, because I know that no matter what, well, what the heck, I'll check. If I take negative 3.5, if x is negative 3.5, and multiply it by negative 2, we're going to get positive 7. 5 plus 7 plus 7 is going to get us 12. And 3 times 12, negative 36 plus 9, that works out. So we're just gunning for a 12 on the inside here. And we could check 8.5. Whoops, bring that back. We could check 8.5. 5 minus 2 times 8.5 is 17. When I take the absolute value of that, I am going to get positive 12. So I know that both of these answers are good to go. They're going to stick around. Let's take a look at Part D. Part D. Okay, well, probably we'd subtract 9 from each side. 107 minus 9 is 98. Equals 2 times some stuff squared. I would next divide by 2. And get some stuff squared equals 49. Okay, that stuff happens to be 5x minus 3. Well, now we could take a square root of each side. And we could say if some stuff squared is 49, that means that stuff must be either positive or negative 7. And I can solve these separately. Either 5x minus 3 is positive 7, or 5x minus 3 could be negative 7. Let's see, here if we add 3 to each side, we get 5x must equal 10, so perhaps 2 is a solution to this. We should check it though. And here if I add 3 to each side, I get 5x must equal negative 4. So x would be negative 4/5, or negative 0.8. So perhaps this is a solution. It would be wise to check these things. If we check 2, 5 times 2 is 10. 10 minus 3 is 7. Squared is 49. So 2 times 49 plus 9. Sure enough, that'll get me 107. If I check negative 4/5, we'd have 2 times 5 times negative 4/5 minus 3 squared plus 9. So good news, these 5s will cancel, and I end up with 2 times negative 4 minus 3 squared. So 2 times negative 7 squared plus 9, and yes, it's the same thing as that. So both of our answers are going to stick around. They're good. Let's move on to number 12, finding equations of lines. Lots of ways to find an equation of lines. I'm going to start by finding the slope. Let's see, my slope is the change in y's over change in x's, or the rise over run. So taking a look at my y values, I went from 1 to 9, and that is a distance or a change of 8. And taking a look at my x's, I went from 9 to negative 3, and that is a distance of backward 12. So I get a slope of negative 2/3. So there's my slope. So we can write y equals negative 2/3. Okay, I took a little breather there, so I know I left off with a y equals negative 2/3. Hopefully I put after that an 2/3 x plus b. So we found the slope, and we need a y-intercept. To find that y-intercept, it would be helpful to know a point, and we know a couple of points. So I'll pick that one and use it. If y is 1 And negative 2/3 of x is negative 2/3 times 9. Let's see, 1/3 of 9 is 3, so 2/3 of 9 is 6, and negative 2/3 of 9 is negative 6. So if we add 6 to each side, I get b must equal 7. All right, so we have a slope and a y-intercept, negative 2/3 x plus 7. It's always good to check, make sure you're right by checking it with the other point. If x is negative 3, I get negative 2/3 times negative 3 plus 7. My 3's would cancel. I'd get positive 2 plus 7, which is 9. So that second point checks out. So we've got ourselves an answer. Let's take a look at part B. Part B says, now can we find a line that is parallel to this one and passing through negative 3617. By the way, this point is deliberately large enough so that you can't graph it. I want you to be able to do this algebraically. And I want you to know that parallel lines have the same slope. And so if you're looking for a line parallel to this one, it must have a slope of 3/4. So y must equal 3/4 x plus some different y-intercept. I could take this xy point and plug it in to figure out what the y-intercept is. 17 must equal 3/4 of negative 36 plus b. Let's see, 1/4 of 36 is 9, so 3/4 of 36 is 27. So negative 27 plus b, and if I add 27 to each side, I get b must equal 44. Let's see, 10, 20, 30, and 14. 44 is my y-intercept. So we have an equation of y equals 3/4 x plus 44. Let's take a look at problema numero C. Number C says, how about perpendicular to this line and passing through 1245? Well, perpendicular lines have reciprocal slopes, and if one is a positive slope, then its perpendicular slope is negative. So they are negative reciprocals. So our slope would be y equals negative 4/3 x plus some mystery y-intercept. Again, I'll plug in the point. I get 45 must equal negative 4/3 times 12 plus b. Let's see, 1/3 of 12 is 4. 1/3 of 12 is 4. So 4/3 of 12 must be 4 times that, so negative 16 equals 45. We could add 16 to each side, and I get b must equal 61. So we have our equation, y equals negative 4/3 x plus 61. Let's take a look at 13. If you are doing this from the worksheet, you will notice that I had to make a couple of revisions. This is supposed to be x minus 5. I apologize for that, but it's fixed on the video. Doesn't help people much who aren't watching the video, though. So here we go. It says, choose two values of x to show that this mess does actually equal that mess. Well, I think to myself, does it? This mess here looks factorable. If we factored the top, it would be x minus 5 times x plus 4 over x times x plus 4. And sure enough, I think that equals x minus 5 over x. So it says pick two values of x and show that they work. Okay, so let's say I pick a number. Let's say I pick 1. Does 1 make this true? Well, if I plugged 1 into this equation, I'd get 1 squared minus 1 minus 20 over 1 plus 4. Does that equal 1 minus 5 over 1? 1 minus 1 is gone, so I get negative 20 over 5. Does that equal negative 4 over 1? And sure enough, negative 4 equals negative 4. This works out. So 1 is a number that works. And if you're thinking, gosh, Ms. Signorati, why don't all numbers work? Then I'm a little bummed because I'd like to think that you know where I'm headed with this. I can't make it shrink down. So maybe I'll try another number. I'll try 2. Is 2 squared minus 2 minus 20 over, what's my denominator? 2 squared plus 4 times 2. 2 squared plus 4 times 2. Does that equal, I think we can look right up here. Does that equal 2 minus 5 over 2? Well, let's see. I'd have 4 minus 2 minus 20 over 4 plus 8. Does that equal negative 3 over 2? 4 minus 2 is positive 2. 2 minus 20 is negative 18 over 12. Does that equal negative 3 over 2? And sure enough, it does, because you could divide top and bottom by 6 here. And you get negative 3 over 2, which equals negative 3 over 2. So it looks like both 1 and 2 make this equation true. If you're wondering what values might make this equation not true, I'm hoping you're recognizing that anytime you divide by 0, all bets are off. And so I'm thinking that if my denominator is, well, let's say my denominator is 0, then this equation would be 0 squared minus 0 minus 20 over 0 plus 0. Does that equal 0 minus 5 over 0? And since both of these are undefined, this is not true. Doesn't matter what is on the top and the bottom. We have negative 20 divided by 0. That does not equal negative 5 divided by 0, because dividing by 0 is undefined. What might be another value that x cannot be? And if you were thinking negative 4, you're correct. Negative 4 is another value that x cannot be. Because when we plug negative 4 in for x, let's shrink this thing. When we plug negative 4 in for x, we get negative 4 squared minus negative 4 minus 20 over negative 4 squared plus 4 times negative 4. And we think that's supposed to equal negative 4 minus 5 over negative 4. Well, the right side of this equation is pretty easy to deal with. This is negative 9 over negative 4, or positive 2.25. The left side of this equation is 16 plus 4 minus 20 over 16 minus 16, which is 0 divided by 0. And 0 divided by 0 definitely does not equal 2.25. So negative 4 is a value for which this function does not equal, or this expression does not equal x minus 5 over x. The end. Number 14 says graph some things. Let's move these guys down here so that I have more space. There we go. All right. Graph some inequalities. Well, this function is a cubic. It is shifted backward 2 and up 2, not forward 2 and up 2. So back 2, up 2. That's my inflection point. From that inflection point, we could go forward 1, up 1, or back 1 and down 1. We could go forward 2 and up 8. 1, 2, 3, 4, 5, 6, 7, 8. It's off the graph. Or back 2 and down 8. 6, 8. And make a swooshy looking graph. I've already screwed up because I see that this is an inequality and not an or equal to, so it's a strict inequality, which means I would represent that with, some dashed lines. So there, we'll make it look a little more dashy. It's dashing now. There we go. So I've got a dashed boundary line, which means my boundary line is not part of the solution. And it says y is supposed to be greater than this function. If you can look at the graph and understand that the shading is going to be above, good for you. If you need to test a point, I think that's a good thing to do also. Maybe I'll test the point 0, 0 and see if 0, 0 works in this inequality. Is 0 bigger than 0 plus 2 cubed minus 2? Is 0 bigger than 8 minus 2? That is not true, so this point is a fail. So every point on the other side works. Let's take a look at part B. Here we have a system of inequalities. One is a circle, and the circle is located back 1, up 1. So back 1, up 1, with a radius of 3. So up 3, back 3, down 3, and forward 3. Let's see, is this a strict inequality? This is a strict inequality, which means my circle should be a dashed boundary line because the circle itself is not part of the solution. If I'm looking for the shading just on the circle alone, I'll test a point. I'll test 0, 0 and see if this makes the inequality true. Is 0 plus 1 squared plus 0 minus 1 squared less than 9? And that would be 1 plus 1 is less than 9. And that is true. So this point works. So we know we're shading the inside of the circle. Now I think what I'm going to do is hold that thought and go graph this exponential function. So it's an exponential function that is shifted up 1. So here is the new asymptote, up 1. From this launch point, the first point I plot is 0, 1, and then 1, 2, 2, 4, or negative 1 up a half. And so we get an exponential function that looks like this. Now we know we're shading inside the circle. Which side of the exponential function we're going to graph is another issue. So let's again test 0, 0. Is 0 less than or equal to the 0 plus 1? Is 0 less than or equal to 1 plus 1? Well, that is true. So that means this side of the exponential function is shaded. So I think we can now deal with all shading. It's going to be below the exponential function and inside the circle. And we have shown all solutions. All right, Algebra 2, hope that some of you find this video useful.